Hello, I'm Rohith Nelson Rajaputi, and today I'm presenting my final project for CS6271, Evolutionary Computation and Humanoid Robotics. This project explores income prediction using genetic programming on a modified adult dataset as part of a Kaggle competition. Over the next few minutes, I'll walk you through the problem, my approach, and the results I achieved. Let's get started. Let me begin with the problem we are trying to solve. This is an adult income classification task, a binary classification problem where we need to predict whether an individual earns more than $50,000 annually based on their demographic, educational, and employment features. The dataset is substantial. We have 39,073 samples and 9,769 test samples with 14 features encompassing demographics like age, gender, and educational attainment and employment details. Now, one important observation I found is that the dataset is imbalanced. The majority class, those earning 50,000 or less, represent 76.1% of the dataset. Meanwhile, the minority class earning over 50,000 represent only 23.9%. This means if we built a naive classifier that simply predicted everyone earns 50,000 or less, we'd achieve a baseline accuracy of 76.1%. So our goal is to significantly exceed this baseline. You might ask, why genetic programming for this task? There are several compelling reasons. Genetic programming evolves mathematical expressions as tree structures, essentially learning the formula that best predicts the income. This offers unique advantages over traditional black box models. First, there's automatic feature discovery. We don't need to manually engineer features. The algorithm discovers which feature matters. Second, the evolved solutions are interpretable, meaning we get mathematical formulas instead of neural network weights we can't understand. Third, GP performs implicit feature selection during evolution, naturally identifying the most relevant features, and crucially, it captures nonlinear relationships and complex feature interactions automatically. To illustrate, here's an example evolved tree. The maximum age of the sum of education number and hours per week. This readable expression shows exactly how classifier combines features to make decisions. The interpretability is powerful. Of course, before we could run genetic programming, we need to prepare the data carefully. Our pre-processing pipeline handles several critical steps. We start with raw data, which contains missing values, categorical features, and numerical attributes with different scales. Step 1 is missing value handling. In this dataset, missing entries are represented as question mark. We applied mode imputation, replacing each question mark with the most common value in its column. This is done for work class, occupation, and native country, the three features most affected by the missing data. Step 2 is categorical encoding. Because genetic programming requires numerical inputs, we convert all categorical variables using label encoding. This is applied to 8 features, including work class, education, marital status, occupation, relationship, race, sex, and native country. Each category is mapped to an integer, making the data fully numeric. Step 3 is numerical scaling. We use standard scaler, which performs z-score normalization to standardize the numerical columns. Features like age, final weight, educational num, capital gain, capital loss, and hours per week are scaled so they share a similar distribution and contribute evenly during training. After these 3 steps, we obtain a clean and normalized data ready to be fed into genetic programming model. After running a series of genetic programming experiments, I selected my final parameter configuration by comparing performance trends across all test runs. I experimented with different population sizes, generation counts, mutation rates, and tournament sizes to understand how each factor influenced accuracy. From the table, smaller populations like 300 or 500 individuals gave decent results, but accuracy consistently improved as population increased. Runs with 1500 individuals repeatedly produced some of the highest accuracies, showing a strong balance between search diversity and computational cost. Increasing the number of generations from 40 to 80 also showed a clear benefit. For example, run 6 using 1500 individuals, 80 generations, and higher mutation outperformed earlier smaller setups. Similarly, consistent use of crossover probability of 80% helped maintain a useful structural mixing, while increasing mutation rate to 30% improved the exploration and reduced premature convergence. Tournament size 7 performed better than smaller tournaments adding stronger selection pressure without causing excessive elitism. The best result in the entire set came after run 8, which matched these settings and achieved the highest accuracy of 0.78. Based on these patterns, I selected a population of 1500 individuals, 80 generations, 80% crossover rate, 30% mutation rate, tournament size 7, and elitism of 10. These final parameters consistently produce the best or near best results across multiple trials, offering a strong balance between exploration, exploitation, and runtime efficiency. And here's how the algorithm actually works, the evolutionary cycle that generates solutions. First, we initialize the population, create 1500 random trees, and evaluate their fitness on training data. Then we enter generational loop. In each generation, we select individuals for reproduction using tournament selection. Better performing trees have higher chances of being chosen. We apply crossover and mutation to create new offspring. We evaluate the fitness of these offspring. We preserve the best individuals through elitism, ensuring top performers are always in the next generation. We update our Hall of Fame, tracking the best solutions ever discovered. Finally, we form the new population and repeat. The benefits are substantial. Elitism ensures top solutions are never lost. We are guaranteed to keep moving or stay the same, never getting worse. This accelerates convergence to optimal solutions, and by maintaining both high quality solutions through elitism and general diversity through mutation and crossover, we avoid getting stuck in local optima while still making steady progress toward good solutions. In this step, we are constructing the core primitive set that our genetic programming system will use to evolve symbolic expressions. We begin by defining a primitive set with 14 input features which represent the full set of variables available to the model. Next, we introduce a suite of binary operators, addition, subtraction, multiplication, and a protected division function, as well as maximum and minimum. These operators give the evolutionary process the mathematical flexibility required to form structured relationship among features. We then add several unary operators, including negation, cosine, sine, square root, and logarithm. Each of the potentially unstable functions is implemented in a protected form to prevent numerical errors such as division by zero or invalid logarithms. This ensures that even as model explores unconventional combinations, it remains computationally stable. To support exploration, we include an ephemeral random constant, which provides an on-the-fly numeric values during evolution, improving diversity in candidate solution. For clarity and interpretability, we rename the automatically generated argument placeholders to match the actual feature names from the training dataset. Finally, we define several protected helper functions, protective, protect square root, protected log, which converts continuous predictions into binary class outputs. Together, these components establish a robust, safe, and interpretable foundation for symbolic modeling within genetic programming framework. Now let's discuss the fitness function. This flowchart describes how the fitness of this genetic program is computed. First, a random but seed-controlled subset of 5,000 training samples is selected so that every individual is evaluated on the same data while keeping the runtime manageable. Using a seed makes this sampling deterministic, which is important for reproducibility and fair comparison of different GP runs. Next, each GP tree in the population is compiled into a callable function, so it can act like a classifier that maps feature vectors to numeric outputs. For, a, for every sample in the subset, the GP function predicts a label. That output is thresholded to a Boolean class and then compared with the true label. The number of correct predictions is counted and normalized to give an accuracy value between 0 and 1. If anything goes wrong during this evaluation, such as numerical overflow or invalid operations, the individual's fitness is set to 0, discouraging unsafe or unstable programs. Finally, this accuracy score is returned as fitness, and evolution then prefers trees with higher fitness, steadily improving the population's classification performance over generations. Here we see how the genetic programming classifier evolves over multiple runs. In the top left plot, the best fitness climbs quickly and then gradually plateaus around 0.86, showing that evolution consistently discovers high accuracy individuals. On the top right plot shows the average fitness across a population, and narrow error bars indicate the different runs tend to converge to similar performance rather than wildly different solutions. Because evolutionary search is stochastic, repeating the experiment multiple times is essential to estimate true performance and avoid overinterpreting a lucky or unlucky single run. On the bottom left, tree sizes grow over generations, with average increasing while best trees stay relatively compact, suggesting that the selection favors simpler but accurate models despite overall load. The confusion matrix shows strong performance on less than 50,000 class, but substantial confusion for greater than 50,000 class, once again referencing to the imbalance in the dataset. Internal accuracy ranges from 0.84 to 0.85, while on Kaggle it was about 0.78, indicating some generalization gap but still solid external performance. The F1 score with precision and recall tells us the model is cautious when predicting high income. When it predicts greater than 50,000, it is usually correct, but it still misses many positives, highlighting a trade off. To conclude, this project demonstrates a successful application of genetic programming to a real-world classification problem. Using the DEEP framework with a custom elitism strategy, the system reliably evolved high-quality solutions, reaching about 85% internal training accuracy and 78% accuracy on Kaggle. These results show that the evolved model generalized beyond the internal evaluation while still capturing meaningful structure in the data. Along the way, the work delivered a robust preprocessing workflow, protected operators for numerical stability, and a well-chosen genetic operator and selection schemes. The final trees remain interpretable mathematical expressions, and the whole setup is reproducible, making the approach suitable for further research and comparison. Looking ahead, there is clear headroom for improvement through stronger bloat control, smarter hyperparameter tuning, and ensemble techniques that combine multiple evolved trees. Future work could also benchmark these GP models against standard machine learning models. Overall, the project establishes a solid baseline GP classifier and a flexible experimentation framework that can be extended in many promising directions. And that concludes my report on this project. Thank you for watching.